Ladies and gentlemen, welcome once again and a very good afternoon to all of you. Welcome to the fourth day of the faculty development program on advances in artificial intelligence. So today the first two sessions will be taken by Dr. Swagatam Das. It's a pleasure to meet him once again and hear from him. Welcome, sir. Uh, I take this opportunity to introduce Dr. Das before all of you. Dr. Swagatam Das has received his BE, ME, and PhD degrees all from Jadavpur University, Kolkata, India in 2003, 2005, and 2009, respectively. Dr. Das is currently serving as an associate professor and head of the Electronics and Communication Sciences unit of the Indian Statistical Institute, Kolkata, India. His research interests include evolutionary computing and machine learning. Dr. Das has published more than 300 research articles in peer-reviewed journals and international conferences. He has 25,000 plus Google Scholar citations with an H index of 75 till date. Dr. Das is also the founding co-editor-in-chief of Swarm and Evolutionary Computation, which is an international journal from Elsevier. He has also served or is serving as associate editors of many uh, IEEE transactions like IEEE transactions on cybernetics, pattern recognition from Elsevier, neurocomputing from Elsevier, information sciences from Elsevier, IEEE transactions on system, man, cybernetics, and so on. Dr. Das is an editorial board member of Information Fusion from Elsevier, Progress in Artificial Intelligence from Springer, Applied Soft Computing from Elsevier, Engineering Applications of Artificial Intelligence from Elsevier, and Artificial Intelligence Review from Springer. Dr. Das has been associated with the international program committees and organizing committees of several reputed international conferences, including Neuro IPS, AAAI, AIS, TATS, ACM Multimedia, BMVC, IEEE Congress on Evolutionary Computation, GECCO, etc. Dr. Das has acted as guest editors for special issues in journals like IEEE Transactions on Evolutionary Computation and IEEE Transactions on System Man Cybernetics Part C. Dr. Das is the recipient of the 2012 Young Engineer Award from the Indian National Academy of Engineering, that is INAE. He is also the recipient of 2015 Thomson Reuters Research Excellent India Citation Award as the highest cited researcher from India between years 2010 to 2014 in engineering and computer science category. I once again wholeheartedly welcome Dr. Das to this faculty development program. And sir, it's over to you to start your session.
Thank you very much, Professor Gyan Ranjan Patro. It's always a pleasure to meet all of you, get back to this nice big institute under Siksha O Anusandhan University. ITR is really doing great these days by disseminating this latest chunks of knowledge to all other faculties who are participating. So what I plan is, since I have two sessions back to back, I will take a break of about 15 minutes around 3:15 to 3:30, and then we will continue with the other part of the session. And since the title of this workshop is pertaining to advances in artificial intelligence, in the first talk, we will look into deep generative machine learning models, especially the GANs. And in the second part, we will look into certain other aspects of machine learning systems when they're deployed practically for several types of purposes, along with their explainability and other issues. Mostly, I will focus on imbalanced classification scenario and explainable machine learning parts in the second part of the talk. If you have any queries or questions, you can, of course, ask me, interrupt me, or put that in the chat box. So let us begin with a lighter note and with the foundational part on generative adversarial networks. Let me share my screen with all of you. Hide share options. Share content. To the organizers, have I been granted the permission to share materials? I cannot share. Hello, am I audible?
Yes, sir, you are audible.
But could you please check, Jan, whether I have been granted the sharing access?
Yes, sir. Give me 1 minute, sir.
Yeah. Yeah, now I think I get that.
Okay, sir.
So could you please confirm whether you can see my screen or not?
Yes, sir, your screen is visible.
Okay. So to improve the bandwidth, let me switch off the camera for the time being. When there will be question answer, I will tap it on. Okay. So as many of us nowadays know, advances in artificial intelligence standing in 2020, 21, 22 typically will mean the cutting edge research that goes on and with deep neural networks and deep learning systems. So, and such systems are finding almost ubiquitous applications all around us in various forms at the back end. And we, in our daily lives, those who have access to smartphones, to different apps like Zomato, Swiggy for food delivery, Uber or Ola for cab, and many other applications. So knowingly or unknowingly, we are using deep neural networks every day. Okay. Now, artificial intelligence, till as you may know, till at least 2000, let's say 6 to 10, till that era, prior to that era, it was mostly driven by intelligent search techniques. But post 2006, after the resurrection of very interesting and very smart gradient-based optimization techniques like the different forms of stochastic gradient descent, this domain of search-based AI had a metamorphosis and it evolved into learning-driven AI or data-driven AI. So see, I first heard that cliche quote that the data is the new oil. You might have all heard of it, but I first heard it in 2011. And in 2012 onwards, 2012 was a remarkable year from where actually all these booms started. I will touch that upon. So post 2012, people started saying if data is the new oil, then deep neural networks are the new engine, which will be driven with that oil acting as fuel. Okay. And since 2014, the era entered into a new regime where we started to talk about deep generative networks. Okay. And these deep generative networks gradually started to exhibit almost human level creativity in certain areas, although there are, of course, quite computation heavy modules or aspects behind them, but they started to show generation process, synthesis process. Okay, not only learning, but maybe drawing a new kind of picture, maybe writing the description of a picture which is being shown to the computer. Very basic skills which are shown even by a human kid. Creative skills, of course, those were started to be exhibited by these sort of new age deep learning systems. And in the first session, I'm going to elaborate on how such systems work. Let me see if I can change my screen. Yes, very good. So in this first beginning slide, the most important piece of data is my email ID, which you can see here. If you require any reference or any suggestion on books and other materials, you can drop me an email over here. Okay. So now, machine learning, as we all know, the term was coined long back in 1959. It means how a learning system is a system which can take right future decisions based on past experience. In case of machine, when I want, machine means, of course, a classical computer fitted with its own central processing unit, and then the stored program concept, one human architecture, and so on. So this computer is expected to take some future decision about category of some objects which may be presented to it, whether a particular picture contains a cat or dog, an ostrich or elephant or what. That decision has to be taken by the machine. So the machine will be shown certain pictures and it will correctly say what is there inside the picture. Okay, so for this sort of thing, the machine will be provided with the voice content of certain people or the fingerprints of certain people, and it must identify whose it is. Okay. So for this sort of, so that is also decision making, basically. It decides the category of the objects being shown to it. So for that, like human beings who get experience from their teachers or parents, similarly, the machine should also should gather experience through some part of the data on which it is going to function. And this part of the data must be previously handled by the user in the form of, the user or the human experts must label that data, must show some examples to the machine, and then the machine based on that should take a decision. That's the objective of machine learning. And it is very different from traditional computer programming, as you can see here. In traditional programming, we give some unsorted lists of integers to the computer and some sorting algorithm turned into a program. The computer, like a clerical staff, executes each and every instruction of that program and sorts these lists in ascending or descending order. There is no innovativeness, no adaptability. But in case of machine learning, we provide the computer with some unsorted lists of integers, and we also provide the computer with the corresponding sorted lists. Okay, that is the dream goal actually, and let the machine figure out how to make a sort, how to sort these integer lists, maybe following certain additional criteria which may be specified by the user, like you must use the minimal amount of memory space, you must execute minimal number of arithmetic operations, and so on. So then the machine must learn how to sort. Let the machine write down the sorting program. That's the goal of machine learning. In fact, automatic program writing is nowadays has become a good part of this learning-driven AI. Supervised machine learning framework, as we all know, works. Supervision means there has to be a teacher. The teacher may be a human expert, like I hire a doctor and I show the doctor 200 X-ray plates with chest X-ray plates with lung X-ray. And from the lung X-ray, there are 3 different types of patients. One are benign, they have no problem in the lungs, they can go home. One have COVID-induced pneumonia, several severe COVID infection, of course, maybe an elderly person. And the other type of patients may have normal bacterial pneumonia. Okay, so the doctor labels these 200 images according to the type of fibrosis or white patches formed on the lungs into these 3 available types. After that, so each patient is put into one of this and take a decision about the category of the patient, whether the patient has pneumonia, if the patient has pneumonia, if it is COVID or normal bacterial pneumonia, or can the patient just walk back home. This decision, this is called computer assisted medical diagnostics. And or a speech signal or video in terms of the most suitable and recorded measured numbers. These numbers are called features, which describe this object or this pattern, something that we want to classify or categorize. X is an abstract representation of the physical object to the computer in terms of numerical features. Y is the category of that object returned by the machine, and F is the magic box. F is the machine learning system. F is a function, okay? And as we know, a function takes as input this X, which is the summary, which is the features of the object that we want to categorize. So X is like the raw material that enters into a factory. That factory is this function or this machine learning system, and Y is like the finished product. So the function returns the category of X. Usually this function must be developed. So every machine learning system could be seen as a function, as a transformation from object to its category, okay? And to build up this function, we require, as I said, the doctor is labeling the images initially. So this set of labeled images is also called training set. So we require a training set, and then how good the machine is doing. For judging that, we provide the machine with a few other previously unseen example images X, for which we may know the correct label, but that correct label is not provided to the machine. Let the machine tell us about the category of these images. This is called testing. Once the machine achieves good accuracy in testing, we can deploy it for unseen data. So this is perfectly what this function is doing. In case of, so from here onwards, rest of my discussion will be mostly for image type data, not for, although all these discussions equally apply to sequential data for like speech, text, etc. But we will mostly confine ourselves to images. And it is really very hard to recognize images by computers. When we look at this image, we immediately know it's a motorcycle because we see handles, wheels, etc. But the camera records piles of numbers like this. Even a small portion of the image is actually such numbers taken together, which specify the gray level intensity. Now, a lot of it depends on how we represent the image in terms of most suitable features. Okay. And based on the context, different features may become important for different types of images, or even for the same image, okay? Even for the same object. I always tell that when I go to a bank and ask for a loan, I am the same object, I become a piece of data to the bank. In my name, there is a file, customer file. So in case of bank loan, my CIBIL score, my fixed deposit amount, my monthly salary, these are very important features which define me. But if I go to a blood bank for donating blood. In that case, probably my age, blood pressure, whether I have diabetes, whether I have any blood-related disease like thalassemia, these things become very, very important. So the same object, but different features may become very important in different contexts. Suppose I mount a camera on the doorway of my garage and I take pictures and I represent each object in the picture in terms of only these two uncorrelated randomly chosen pixels. So every image becomes a point in this two-dimensional space. Along x-axis, value of pixel 1, along y-axis, value of pixel 2. So what will happen? Even if the picture doesn't contain any car, maybe two dogs are walking in, or one monkey is going into the garage. If that happens, even then, these are non-cars versus cars when the car is going. So if a non-car object walks into the garage, there should be some alarming. Okay. But the problem is, since these two pixels are completely decorrelated, cars and non-cars will get completely mixed up, prepare a khichdi-like structure. On the other hand, if we could have done some, we could have devised feature detectors, 3x3 or 5x5 submatrices, small windows with very judiciously chosen coefficients, such that when one such detector is dragged over the image by using nested for loops, if that detector finds out a handle-like structure, it will record a very high response. And if the other detector detects a wheel-like structure, it will record a very high response. These are handle and wheel detectors. If we drag these two detectors over the image and simply add their responses, the non-cars will have very low response for, sorry, if we just plot one response along x-axis and the other along the y-axis, and then we define a two-dimensional space, then naturally the non-card entities, these red minus signs, they will accumulate very near to the origin, and the card entities, these plus signs, they will accumulate far away from the origin. And in between these, we can actually very easily, even with a linear classifier, we can separate them. So you see, separability of different classes, how well a classifier will work, it depends a lot on how judiciously we are representing different objects in terms of a set of numbers sitting together, which are called higher level features. So here, pixels are the lowest level features. They are like the machine language program. And the abstract and higher level features are like whether there is a handle, there is a wheel, there is an engine pipe. These high level features could be found out by manipulating these pixels through linear, nonlinear combinations. In fact, every convolutional neural network, CNNs, basically evolve such, they fine-tune such, feature detectors based on which they find out these abstract and high-level features. And visual classification is a very tough job. Human mind is very great at it. It's a great expert. By looking at these images for some time, you can immediately tell me which one is a mop and which one is a sheepdog. Similarly, which one is puppy or which one is bagel. These are very tough, benchmark data sets for deep neural networks. Or which one is an apple and which one is a barn owl. So you see, here also, not only that you tell us which one is what, but you can tell me based on what feature you are differentiating. The owl has two eyes with great distance apart, but the seeds of the apple are so close. The owl has a ridge-like structure in between, which is the nose. And the apple has a different fold between the two seeds, etc. Similarly, which one is a chihuahua and which one is cherries on the cake? Maybe you can tell me, okay, for the dog puppy, the eyes and nose are arranged on the vertices of a regular triangle. So usually based on such higher level features, we make the distinction. Okay? And it it is indeed very important. So deep neural networks or deep learning systems have evolved to mitigate this problem of suitable context-aware representation of different objects, which will make the classification a very easy task. So this abstract higher level representation of objects in terms of most suitable higher level features is the biggest selling point of deep learning. And deep learning works like a, this modern crow who will use this straw to deep learning is that assistive technology, that straw, which will save a lot of effort from, instead of using older technologies. So I think there is some mic which is not, which is creating some noise. So maybe you can, for the time being, think of muting yourself. There is a mic which is creating some noise, I think. Shrey Mittal, could you kindly mute if you don't have any question? Okay.
Sir, can you explain this higher level and lower level feature a little bit elaborately?
Yeah, sure. So first of all, when you look into a picture, let me share it back. Just give me 1 minute. Somebody is at my door, so I need to open up the door and check. Probably some parcel has come. Just 1 moment. Yeah, let me share back my presentation and then I'll explain. So first of all, you see one thing. When we say higher level programming language or lower level programming language, what do we mean? Low level programming language is like the machine language, okay, which is very close to the machine, which the human beings cannot interpret easily. And higher level programming languages are usually written in such a way, the syntax is in such a, it comes in such a fashion that the human beings can interpret it very easily. They are close to human beings. So in case of machine learning also, when we look into an image just in terms of such pixels, when the camera looks into the image in terms of such pixels, it's a pile of numbers. These pixels are close to the machine because machine understands nothing but numbers. But to get a typical classification between whether it's a car or whether it's nothing, it's not a car, it's something else, a tree or a sky. For that, we require some higher level and more abstract feature. Higher level means these are not merely numbers. These are some shapes, some edges, some specific geometry inside the image, like these round shaped wheels, like the pipe which looks like a cylinder. So presence of these things will indicate that the object is a car. Okay, so these higher level objects, higher level once again, because these are interpretable by human beings. These are close to human interpretation. That's why such presence of such geometric shapes, specific edges, etc. These are high level features. So, and the high level features could be automatically learned in a deep neural network. CNN basically does that. That's the selling point of it. And based on such representation of the object in terms of its abstract and high-level features. When you look at the face of your friend, you don't look like, okay, the top left corner pixel is 233, let's put that 146, never. You immediately recognize whether the person has a nice mustache, there is a cut mark on the chin, there is a mole near one nose. These are the high-level features. Okay. And based on such features, you recognize the person after 2 years when you see him face to face. So if you don't, if another mic is creating some noise, kindly mute yourself, okay, if you are not asking anything. So this is the difference between higher and lower level features. And as I said, I can hear a lot of noise. Kindly mute yourself if you are not asking any question.
It's a request to all the participants. Please kindly be muted when the talk is going.
I can see lot of noise.
Ma'am, one suggestion, ma'am. Ma'am, organizer can mute all the participants, ma'am, except the organizers team.
Yeah, I think that's fine.
There is an option, ma'am.
Okay, so let me continue. So in traditional machine learning, there is a human feature extractor who actually combines the lowest level, like this pixel level features in various ways to generate the more abstract and high level features. And for over last 30-40 years of history in computer vision, video analytics, etc., there has been various, handcrafted feature extraction techniques like scale invariant feature transform, histogram of oriented gradient, text on, Gabor filter. All these techniques actually work very well for one particular type of image, but not so well on other type of image. So many types of images have to be handled from real world, like medical images, natural scenes, radar aperture image, so many types of image, synthetic aperture radar image. So in such cases, there is no universally good handcrafted machine learning technique. And deep learning actually gets us rid of this human feature extractor. Okay, so there is no handcrafted technique which needs to be applied on the input. Sometimes such techniques can work well alongside the deep neural network, but the deep neural network system is a system of such interconnected layers of very simple processing nodes, which are also called neurons. And the inputs are basically the lowest level pixel level features, okay, which are recorded by the camera or some other sensing equipment. These lowest level features, while flowing through these links like the signals, they get amplified or attenuated, combined in linear, nonlinear fashion to give rise to abstract and higher level features. In fact, convolution, discrete convolution sum, which is used in convolutional nets, is a way of such combination that gives rise to abstract, higher level and context aware features. Those higher level features which are most important for this classification, car versus non-car, presence of pipes, wheels, steering, these will be very important. Birds versus non-birds, in that case, presence of feathers, a long beak, these will be very important, okay? If you change the context of your classification, the features will also change. The importance of different features will have a big shift, okay? So now coming to gradually, we are moving into our point. There are two deep inference models which are very popular nowadays. One is called predictive deep inference model, and the other one is called generative deep inference model. In case of predictive model or discriminative deep learning model, the classifier is happy to learn a decision boundary in a proper feature space between the points from the two classes. It's much like this. The discriminative model is happy to learn this Lakshman Rekha, this decision boundary between objects, between the objects from two classes. On the other hand, the generative models, they not only classification is secondary for them. What they try to do is they try to estimate the underlying probability density function or the probability distribution. They try to closely approximate the probability distribution from which the objects from these two classes might have been sampled. Let me tell you one thing very carefully. Data in this context, data to a computer scientist, what is data? If I ask you, you have heard data so many times. Anything around us which could be abstractly represented, stored, and processed by a computer in terms of bits and bytes. That means anything which is represented in terms of suitable numbers and stored and processed in the computer, which could be myself or any of you also. As I said, when you go to a bank, you become a customer record. So all these are pieces of data. But to a statistician, what is data? How many of you might have heard of the term random variable? I think many of you might have heard of the term, right? So a random variable, put it very simply, a random variable is a variable. Variable means something which is varying, doesn't have a fixed value. And random means no one knows how it is actually exactly varying. What will be its value after 3 seconds or 3 days? No one knows. It will be random. It is not deterministic. But the randomness still obeys certain probabilistic rules. The theory of probability tries to formalize such rules. Okay. So this, in case of statistics, data is an instantiation of a random variable. So there is an underlying random variable which is varying randomly. And as we observe, as long as we do not observe, we do not measure that random variable, it is uncertain. But when we observe that random variable, it becomes a certainly known historical value. That is your data. So if I say how many days it rains in the month of December, now the weather is so much changing in Calcutta, huge rainfall in December. Anyway, so how many days will it rain in the month of December in 2015, 16, 17, 18, 19, 20, etc. So my random variable is how many days it will rain in Bhubaneswar or in Kolkata in the month of December. That is the random variable. Now, last 5 years, if you have observed this random variable, maybe in 2015, only 1 day, 2016, 0 days, 2017, 3 days, 18, 9 days. So now this number of days it rained in past in the month of December, these are the observed value of the random variable. And this is your weather data actually. This is a weather time series data, okay, because it varies with the year. So under every data, there is a random variable, and that random variable is varying. As we observe that random variable, now or in the past, it becomes data. This is the interpretation of data to a statistician. So the generative models try to, capture the underlying rules that govern the variation of this random variable, multivariate random variable, because it has multiple features, and the random variable is a vector in this case. Every image is a high dimensional vector. And generative models try to estimate this high dimensional underlying set of rules following which these data may vary. Once it gets hold of these stochastic rules, or once it can approximate this underlying distribution, it can sample from the distribution and create artificial objects, artificial images, artificial speech signals, artificial text documents, which will not be carbon copy of any such thing shown to the system, but which will be very, very realistic, though artificial. I will tell you why I am saying this. So the generative models try to, the deep generative models are the top discussion topic now. among which we have this generative adversarial network and also variational autoencoders. They try to solve an age-old problem from statistics. What is that problem? If I give you, so once again, this is a very important point actually. That's why I'm sticking to these slides for so long. So once again, if I tell you, many of you might know this, density estimation is an age-old problem in statistics. I give you 10, 20 scalar numbers, 3.8, minus 4.6, 4.88, and so on. And I ask you, return me the Gaussian probability density function or the normal density function from which these numbers have been most likely to be sampled, most likely have been sampled. So you will immediately apply a maximum likelihood estimation or MLE algorithm, which is good enough to find a very close answer. Find the mu and sigma, mean and standard deviation of the Gaussian. But instead of 10 scalars, if I give you 10 high dimensional vectors, each of which may represent an image, even if your image is 100 pixel by 100 pixel, it involves 10,000 dimensions. Okay, so you can pack all the pixels in a vector and the vector may have 10,000 dimensions. So if I give you this 10,000 dimensional object and ask you, now tell me the underlying probability distribution or density function from which these objects might have been sampled, no guaranteed statistical method can solve this problem. Therein where neural network comes to rescue, and therein how GAN was created. Generative adversarial network was created. So I think all of you by now know what is deep neural network. In 1980, before I go to GAN, just let me give you couple of slides on structure of deep nets. In 1980s era, the neural network used to look like this. Nobody cared about hidden layer. Only 1 or 2 hidden layers are good enough. Any function, nonlinear function, could be approximated by such neural network. And these links are carrying the signals from one node to another with amplification or attenuation. However, post 2012, everyone was busy in increasing the number of hidden layers in their neural network structures because it became gradually very clear that the hidden layers are creating the magic. The hidden layers are combining the lowest level features or camera recorded features, that means the pixels, into edges. The edges are then combined into more intricate parts of your image. For face image, they may be like nose, eye, brow, cut mark on the chin, thereby face parts and thereby complete prototype of the face, matching against which a classification decision will be made. Okay. So I was talking about 2012. In 2012, Alex Krzyzewski, Sutskever, and Geoffrey Everest Hinton. Hinton was also the person who was behind the development of the back propagation algorithm in its formal form, the form we know today. And the same Geoffrey Hinton, he is one of the father figures in deep learning. So he and his 2 students came up with this deep convolutional neural networks for classification of a huge data set of images containing 1.5 million images, 15 lakh images, distributed over 1,000 plus classes. And this network actually achieved an error rate of 16% on the top 5 classification accuracy on ImageNet. And before this network, the error rate was 30% by shallow learning models like random forest or best variants of support vector machines, etc. So this paper in the famous NIPS conference, Neural Information Processing Systems conference, marked the beginning of deep learning. This network later evolved into AlexNet, which was acquired, I think, by MATLAB. AlexNet was the first prototype deep network inside MATLAB. Then gradually Python came into picture and took the whole market, in machine learning at least. In fact, from 2012 onwards, these companies, giant companies like Google, Amazon, Facebook, Samsung, every big company, Adobe, HP, all of them started investing huge amount of money for the development of such deep neural learning systems, as a result of which the depth also increased, because as you increase the number of hidden layers, the optimization of the network becomes very, very tough. So in 2015, the same ImageNet classification challenge was won by Residual Network, or ResNet, which had 152 layers. And it dropped down the accuracy, the error to only 3.5%. The accuracy was about 96.5%, which was indeed a groundbreaking result at that time. That's why ResNets are nowadays also very, very popular. What happens inside a convolutional net? Once again, you give an original image as input through repeated operations called convolution, followed by a ReLU network, ReLU layer. ReLU is a nonlinearity, all of you should know, rectified linear unit, followed by downsampling through max pooling. So mainly convolution and max pooling. The image, which may be, the original image may be 1000 by 1000. That means 10 lakh pixels are there. So from there, through the repeated application of convolution and max pooling, it reduces to a vector, which we call flattened feature map. So it reduces into such a vector, which may contain only 500, 600 entries inside. So from 10 lakh to 500, or even 200, each of the numbers inside this vector, which is obtained after layers of convolution and max pooling, these numbers actually specify some very important coded high-level features in the image, like different color of feathers, a beak, what is the position of the beak, what are the other, is there a tail? So these sort of higher level features are encoded inside this vector. And this vector finally goes into a fully connected regular neural classifier with very few hidden layers, as you can see here. And this architecture is outputting the proper class level of this input object. So before the final fully connected layer, what is happening? A vector goes, an image goes in as input, and a vector of higher level features comes out as the output. That is the convolutional flow. If we reverse the flow of the CNN, then we have something like this. In that case, our input will be a vector and our output could be an image. There is a mechanism to reverse the flow of the CNN. This is exactly the way how the decoder part of an autoencoder functions. I don't know whether autoencoder has been covered here or not. So this is called deconvolutional flow. In convolutional flow, before the fully connected network, we have image as input and a vector which is supposedly containing the abstract and high-level features of the image. That vector comes out as output. In deconvolutional flow, we have a vector as input and finally an image as output. So the deconvolutional flow generates an image from the coded vector. Now there comes GAN. It was a 2014 breakthrough. It was published in 2014 NIPS conference. This 12,000 is a very old number here. Now it has almost 40,000 citations. Okay, a number which we cannot gather in a lifetime. So this paper alone has got, and it's hugely used everywhere. So, and as you can see, the quotes from Jan LeCun, the director of AI research at Facebook, that this is the most interesting idea in last 10 years in machine learning. Okay, so let me go straight into what GANs try to do. Once again, their main emphasis is not acting as a classifier. Their main emphasis is synthesizing very realistic but fake images, speech signals, videos, text documents, and whatnot nowadays. even inter-domain conversion. Convert an image into a suitable text description, convert a text paragraph into a suitable image matching that description in the text. All these magics can now be done with GAN-based tools. Okay, so let's develop a first understanding of how the vanilla GAN works. This is most important. The foundation is always the most intricate part of anything. So the objective of this session is to equip you with the background knowledge with which you can yourself read the rest of the literature. It's huge, really. So probabilistic generative models, from real world we get observations. What are observations? Once again, statisticians, we call image, we call text, we call a data. Statisticians call them observations because they are the instantiation of some underlying random variable. That's why observation is a nickname to data. So from the real world, we have some example data. GAN, if I show GAN a number of bedroom images, real bedroom images with different linens, cots, windows, designs from most luxurious suites of world famous hotels, GAN can generate its own bedroom images, which will not be carbon copy of any image shown to it, but which will look like very realistic photographed image. No such bedroom actually does exist. That's the dangerous aspect of GAN. Okay. So to enable it, we need to show it some examples. It's like you are showing some human kid lot of example houses, and then you are asking the kid to draw a house like structure on its own. So the kid will able to do that. If the kid has good imaginative power, the kid will come up with a nicely drawn house, which is not exactly a carbon copy of what you have shown. So from the real world, we have observations. Okay, and observations means example data. And from the model, we will have synthetic observations. The goal of modeling is to match these two. And the density estimation means the probability density function which governs the observations should also be equal to the probability density function of the synthetic observation. So I will just, this is, now let's come to GAN structure. Let's get into the anatomy of GAN. Inside GAN, there are actually two neural networks. One is called a generator network. The input of the generator network is a initially randomly chosen noise vectors. So they may be 100 by 1 or 200 by 1 floating point number vectors. Vectors containing floating point numbers. The generator converts these vectors into images. So the generator outputs are images. On the other hand, so the generator creates lots of images. On the other hand, there is another neural network which acts like a two-class classifier. This neural network takes an image either from the generator or from a real-world repository of training images. Like all other neural network systems, GANs also require training images. So the discriminator may take images from real world or from the generator, and then the discriminator, its input is an image and its output is a scalar number between 0 and 1 in that scale of 0 and 1. So if the discriminator feels that the input image is very poor, badly generated, must be fake, then it will assign a very low score like 0 or 0.001 or 0.05, something like that. On the other hand, if the discriminator feels that the input image is very good and it's a real image, then it will assign a high score to it, like 1 or 0.9, etc. So the generator takes code vectors and creates this sort of images. Okay, who can act as a generator? I just showed you a few slides back. The generator could be nicely made by using a deconvolutional neural network, or even by using the decoder part of a standard autoencoder. Okay, On the other hand, so these are the images generated against different codes. So the neural network generator generates an image from a code vector, and the image should look like a real code vector as much as possible. Sorry, the image should look like a real image from the training data as much as possible. That is the goal of the neural network generator, to make the generated images in spirit similar to the training images shown to it. On the other hand, so you can contrast this against the neural network classifier. What does the classifier do? If it would have been a classifier, you would show the image to the classifier, and the classifier would generate a one-hot encoding of the class of this image. One-hot encoding means there are 10 entries in the output vector, and the entry corresponding to this class to which the input image belongs should be 1, and rest of the entries should all be 0. So since this image is probably a 1 written, so these are handwritten digits. So in that case, the output should be like 1 and 0, 0, 0, all 0. So the neural network classifier tries to match the output vector with the actual one-hot encoding of the class. On the other hand, the discriminator is another neural network which could be very easily, now in fact, discriminator, once again, it could be even a logistic regressor. It acts like a two-class classifier, and the discriminator takes an input X. The input could be an image. The output of the discriminator is a scalar number which represents how good the object is. Okay? As I said. So if it's a very bad object, as you can see, with very bad image like this, the discriminator will give it a very poor score. Otherwise, it will give a score close to 1. It is also called evaluation function, potential function, etc., etc. In GAN, we try to use the discriminator's feedback to generate better quality images from the generator. So now let's see the process. The discriminator training goes through this process, given a set of positive examples. These are the positive examples, which should, positive means good, better quality images, actual images, which will come from the real world training set. Now, since the discriminator is supposed to act like a two-class classifier, we should also provide it with very bad examples, very poor quality images. Where from they will come? Think of it. For the training of the discriminator, I want to make the discriminator aware of, okay, these are the real world images and these are very poor fake quality images. So initially, these fake images come from the untrained generator. So in each iteration, learn a discriminator D that can discriminate positive and negative examples. So the discriminator discriminates between these nice real world images versus these poor images. These poor fake images are generated by the untrained generator, and the discriminator learns to discriminate between them. Usually, now how we generate these poor images, these negative images, they are generated, the generator generates a number of images, and initially the generator is untrained. The generator acts like a kid who has no idea of how to draw something. So the kid just draws some random patterns on her drawing sheet. So this untrained generator creates a number of images, and these images are fed into the discriminator, and the discriminator assigns them some poor scores. Among the poor scores, the maximums could be taken up. Maximum score based 5, 6 images could be sampled, or 4 images could be taken in a batch, and 4 other images could be taken from the real world training set. Then these 4 to 4, 8, total 8 images form a batch training set for the discriminator. And the discriminator is trained on this batch. Okay. Now discriminator weights are updated through backpropagation based training on this batch. So the generator actually generates this image X tilt. This box means the generator generates a lot of images which are denoted as X tilt, and those X tilts are chosen which gets maximum score from the discriminator. So generating negative examples, the NN generator generates an image. The discriminator provides it a very poor score. This image is not shown to the user, hence it's a hidden image. In fact, once the discriminator is updated, after that, the generator uses this trained discriminator to create better quality images. So the generator is updated until it can get a high score from the discriminator. Once the discriminator is trained, this trained discriminator is fixed, and the generator is updated by relying on the feedback provided by the discriminator. Why gradient ascent is used for generator update, I will come to that. Okay. So now, before I take a break, you should think of that. We have two neural networks at our disposal. These two neural networks are actually competing with each other. They are like in a tug of war game. The generator creates lots of artificial images, initially which are very, very poor. The discriminator gives them very poor feedback, just dismisses all of them. So the generator, and for that the discriminator of course has to learn how the real world images, how beautiful the real world images are compared to these fake images. So once the discriminator is learned, this trained discriminator is used to judge the generator. And the generator tries its best to impress the discriminator until it gets very good score from the discriminator. After that, this improved generator is used to create negative examples for the discriminator, and more real-world examples are fed into the discriminator training so that the discriminator may learn finer levels of distinction between the real and the fake images. Thereafter, even more, meticulous, even more better learned discriminator is used to give feedback, even harder feedback to the images generated by the generator, and the generator again improves itself until it matches, until it gets very good score from the discriminator. So it goes on and on. The two neural networks compete. They try to improve each other through this algorithm. That's what I'm going to tell you. So we initialize the generator and the discriminator with random weights and biases. In each training iteration, what happens? We sample some real objects like this. The generator is here. We generate some fake objects by using the generator. These fake objects are labeled as zeros and the real objects are labeled as ones. This training set of, in this example, only 8 images have been used. So this training set of 8 labeled images are used to update the weights of the discriminator. Once the discriminator training has converged, the discriminator is making no error in training set. Training error becomes 0. That means the training has converged. Now this updated discriminator is used to give feedback to the images generated by the generator. And the generator is continued to be updated until it receives very good score from this discriminator. Once the generator updation process ends, this updated generator is used to create even improved fake objects in the next round, which are again labeled as 0. And this new training set is used to train the discriminator so that it can learn finer level of distinction between real and fake images. It's like the discriminator is like a teacher. The teacher is giving feedback on answers written by students of the school. The students are trying their best to impress the teacher so that the teacher gives 9.5 out of 10. It's a literature subject, let's say. Teacher is initially the students did a lot of wrong things, bad sentence construction, poor literary flavor, spelling mistakes. So the teacher gives only 4.5 out of 10. After a few rounds of correction, now the teacher thinks the students have done good. So the teacher is giving them 8, 8.5, etc. Then the teacher participates in a district teacher training camp, where the teacher comes face to face with many other teachers of the same subject from other school, and the teacher learns how the other, famous schools of that area, how the first boys, first girls are doing over there. So now the teacher comes back to the school with this new exposition, new experience, and the teacher is now even harder on the students. The teacher is imposing even harder criticism on the answers written by the students, and the students are again improving themselves so that they can beat these famous school students. I don't know whether this example you understood or not, but this is a perfect analogy between how the generator and the discriminator are improving each other. So this goes on, and this part is the learning of the discriminator, and this part is the learning of the generator. Through this process, actually from the terminology of game theory, we say the generator and the discriminator are playing a two-player zero-sum game. Two-player zero-sum game means if one wins by ₹10, the other one will lose by ₹10. So their net profit is always 0. On one side we have +10, on the other side we will have -10. That is the two-player zero-sum game. So now let's look at. Yes, is there a question? Hello.
Meeku bundle kavalna? Suresh sir.
Hello. I can hear some noise.
Okay.
Hello. If you are asking a question, I cannot understand. Shall I continue?
Yes, sir.
Am I audible?
Yes, sir, you're audible.
Okay, so as I was telling, the training of the GAN could be seen as a two-player zero-sum game. The generator network is trying to fool the discriminator by generating real-looking images. The discriminator network tries to distinguish between real and fake images. And they are, now for training the neural networks, we require an error function or an objective function. That objective function must be, optimized by using gradient descent type algorithms in batch mode or online mode, in stochastic mode. In case of GAN, the objective function takes this form. There are two sets of parameters, weights. Parameters means weights and biases. Theta D is the set of parameters for the discriminator network. Theta G is the set of parameters for the generator network. And the minimax objective function looks like this. E, this calligraphic E stands for an expectation operation. Expectation is a statistical operation, but here, in case of finite training sets and discrete training examples, the expectation will be approximated by simple averaging. So we say, okay, we take some images from the real world data set. P data is the underlying probability distribution of the real world data set. These X's are coming from the real world data set. These are training images. That's why this symbol is used, X tilde P data. Log of this capital D of X means what is the score given by, this is a logarithm of the score given to the real data by the discriminator. Then Z is a codebook vector which serves as the input to the generator. G of Z, G of theta G means for theta G parameters, what image is generated by the generator G. So G of Z is the image generated by generator G when the input is Z. D of G of Z is the score given to that fake image by the discriminator whose parameters are theta D. 1 minus that score is of course, reverse of the score, and log of that is the logarithmic score, logarithmic reverse score. So think of it. Now the discriminator, how should a good discriminator behave? It should maximize this first term, log of d of x, when x is real world data. So on average, this logarithmic score must become a maximum. Then for a good discriminator, d of g of z should be very small because g of z is a fake image, and 1 minus d of g of z should be therefore very large, close to 1. Log of the same thing should also be very large, close to 0. Otherwise, it's actually negative. So with respect to the discriminator parameter theta d, both of these terms must be maximized. So the discriminator output for real data x is here. Discriminator output for generated fake data gz is here. And the discriminator theta d wants to maximize both the terms. That's why it's a max problem with respect to theta d. Discriminator wants to push the term d of x towards 1 and d of g of z towards 0. On the other hand, the generator has nothing to do with this first term. Because you note, among the two neural networks, the real world data is provided only to the discriminator and not to the generator. Therefore, generator has nothing to do with the first term. The generator only wants to generate so beautiful images gz for which d of gz should be very close to 1. And therefore, log of 1 minus d of gz should be very close to 0. Sorry, 1 minus d of gz should be very close to 0. Log of that should be very small negative number. So generator wants to minimize the objective such that d of g of z is close to 1. That's why it's a minimization problem with respect to the generator parameters theta g. That's why when we optimize this objective, when we train the discriminator, what we do? We do gradient ascent. Gradient ascent is nothing but gradient descent with a negative sign on the, instead of negative gradient, we are using the positive gradient direction. Now we are going up the hill. We are not down the hill. So unlike steepest descent, we are using steepest ascent because we are maximizing, right? So when we are training the discriminator, we are using gradient ascent in a back propagation for a framework. On the other hand, when we are training the generator, we are using gradient descent on the generator because it's a minimization problem. And gradient descent, only the second term is good enough. Okay. So, okay. But there is a problem now. The problem is, if we look at this objective function, we are minimizing log of 1 minus d of g of z. You know, for convergence of gradient descent, the gradient magnitude should be good enough. Only then the weights will rapidly get updated and finally converge. But if we plot log of 1 minus d of g of z versus d of g of z, you see a curve like this blue curve. What is the problem of the blue curve? The problem is this region between 0 to 0.8. In this region, d of g of z is actually small, 0.2, 0.3. That means the generator is actually doing bad. Gz is such that d of g of z is small. So in this region, we require rapid update of the weights of the generator. We require harsh punishment of the generator weights because it is doing bad. But in this region, the curve is very flat. Due to this flat nature, if you try to draw tangent on different points of this blue curve, the tangents are very flat. The slope of the tangents are close to 0. That means the gradient is very, very small. due to such small partial derivatives or gradients of the error function with respect to different weights, the update of the generator parameters could be very slow when the generator is doing bad. But actually in this region, we require fast update. On the other hand, when the sample is already good, here post 0.8, in this region, GZ is such that D of GZ is 0.9, 0.85, so it's good. So there we have a high gradient signal. Actually, here we do not require to change the weights very fast. So to alleviate this problem, what we could do in the actual GAN's paper, a very nice solution was proposed. They said, okay, instead of minimizing log of 1 minus D of G of Z, how about maximizing log of D of G of Z? So if we take log of D of G of Z, we get this green curve. And for the green curve, it's just a kind of mirror image of the blue curve, and it has a rapidly changing portion here when the D of G of Z is quite low. That means it's a high gradient signal. Here, if you draw tangents at different points, see my cursor. If you draw tangents at different points, the tangents will change the slope very, fast. That's why instead of gradient descent, we also use gradient ascent on the generator with a different objective. So that different objective is here. We maximize this log of D of G of Z with respect to theta G. And finally, this is the algorithm. Now you see here we have used this expectation notation, but here what we are doing is we sample mini batch M of noise samples from some random uniform or Gaussian random distribution. We just initially take up these random noise samples. We sample a mini batch of M examples from the data generating distribution P data, and we update the discriminator by ascending its stochastic gradient. So we take sum of all these logarithmic scores and reverse logarithmic scores over the M samples. Then we divide by the number M. That is basically a proxy for the expectation operation. Now we take the stochastic gradient of this entire objective function and we update the discriminator weights. Similarly, we update the generator weights by using this average logarithmic score. Okay. And we go through stochastic gradient ascent in both the cases. Okay. So I think I will have a brief this part before I switch the topic slightly. Let me show you some results on the GAN systems and yeah, so as I was saying, this is the training methodology of GAN, the complete training loop of the vanilla GAN. Although thereafter several changes have been done to the GAN algorithm in various forms. The GAN codes are available very well, but they usually take a lot of time on simple computers. There may be three situations in the training cycle of GAN. One is the false negative scenario. So what happens in the false negative scenario is a real image is given to the discriminator and the discriminator weights are not that good. So the discriminator assigns it a high score. Sorry, gives it a low score. That means the discriminator treats the real image as fake. So in that case, if that happens, then the discriminator weights will be updated. That means the discriminator requires punishment in the form of tuning of its weights. Then the true negative scenario where the generator generates a fake image and the discriminator treats it as fake. So the discriminator rightly gives it very poor score. So now the generator requires updating. So based on the gradient of the error function, that log of d of g of z term, the generator weights will be updated. And the third scenario is the false positive scenario, where discriminator treats a fake image as real and therefore it requires tuning of its weights. Usually the training cycle of GAN involves these three scenarios. This is another schematic diagram showing you how the training samples are updated, how the discriminator is updated once, and then the generator is updated, then again the discriminator is updated, and how this cycle goes on. This is just a glimpse of a simulation where we show that the real data is arranged on the blue circle, and the orange data points are the generated data. So the generated data tries to approximate the real data distribution by arranging them on the blue circle. And the convergence criteria, convergence characteristics of GAN is better, but GANs are not meant to work on such two-dimensional, very simple data. They are meant for something else, like this. So in this picture you are looking at, so you see GANs were trained with lot of horse images, sofa set images, bus images, church images, and so on. And after such training, GAN generated its own horse images, its own sofa sets. These are the images synthesized by GAN. Buses under different backgrounds, churches with different backgrounds, cycles. All these images, although they look like somebody has camera photographed them, but they are all fake. They were never clicked on any camera. Okay. Similarly, you see how the GAN images evolved with time, because since 2014 till date, we have very, very well performing parallel computing architecture, very efficient GPU clusters, tensor processing units by Google, TPUs, and so on. So with the dramatic growth in the field of computing hardware, the GAN images have also, nowadays the GAN training could go on for huge number of cycles or epochs, and as a result of that, the GAN generated images have also become almost photorealistic. So this lady, you can see her gray hairs, her wrinkles, etc. This lady doesn't exist on Earth. Nobody actually clicked this picture. This picture was synthesized by GAN for a ghost lady who doesn't exist. Do you get my point? So this is something which could also be very dangerous in generating. Nowadays, GAN can generate lots of fake news, fake video, fake image. These have very nice applications in movie industry, special effect, in imbalanced classification, in scenarios where the training data is very small. But like all other branches of science, now they could also be misused in a variety of ways. That's why the topics like artificial intelligence and ethics, ethical responsibilities of the researchers have become of paramount importance these days, because tools, this sort of synthesizing tools with which you can generate artificial videos, fake images, which could trigger out a riot somewhere. So the correct and ethical use of such tools must be promoted. Okay, not only human faces. The recent Big GAN project from DeepMind. DeepMind is a section of Google which are, which is dedicated towards this this sort of deep learning research. And GAN could generate several artificial images of different classes of the ImageNet dataset, and with better than before quality. So all these images, they were never photographed. Do you understand what I'm saying? They were never clicked by any human being with any camera. They are all fake. They are generated by GAN. This is very interesting. not only this, so a new GAN is coming almost every week. Almost every week we see a new GAN. Now I will discuss one application of GAN to class imbalance, but for that I will have a different set of slides. Now we just go to something else. Yeah. Cycle GAN, for example, in 2017 ICCV is the biggest conference of computer vision from IEEE, and CVF, Computer Vision Foundation. So ICCV 2017 saw this paper. This paper was published by people from Berkeley, which says unpaired image-to-image translation using cycle-consistent adversarial network. So what is happening is that, in fact, the paper begins with this picture. Cycle GAN is a system of two GAN architectures which can convert one image, which can actually, sorry, not exactly convert, which can actually impose the style of one image into the other image while keeping the content of the other image same. So you see, Cycle GAN is trained with this sort of drawing styles, painting styles by very famous artists like, just hold on, I have just one phone to take. Just give me one moment. Hello. হ্যাঁ, 5:30 হ্যাঁ, ঠিক আছে. Yeah, sorry for the interruption. So you see, Cycle GAN has been trained with images drawn by famous artists like Claude Monet, Vincent van Gogh, Cézanne, Ukiyo. And then if you take the photograph of some scenery like this one with your camera and you provide it to Cycle GAN, it could convert the image into as if the same landscape was painted by Vincent van Gogh or Claude Monet. Similarly, it can convert summer landscape scenery to a winter landscape scenery. It can convert zebras to horses. It can convert a Monet image or an image drawn by Claude Monet into an original photograph, as if clicked by camera, and vice versa. These are the style transfer problems. So nowadays, eye-to-eye, image-to-image translation has become one of the major advances in this deep generative technology. Okay, not only image to image. Now, as I said, we can also translate, convert from one domain to another domain. You see, this paper was published only 4 years back. After that, tremendous development has happened in this particular area. And as a result, for example, this neural photo editor, where you can put your cursor anywhere and it shows how the hairstyle changes. Pix-to-Pix is another eye-to-eye translation system. It was, I think, sort from CVPR paper 2018 or so. Pix-to-Pix GAN, if you give this search, you get a lot of things to see. So this architecture can convert black and white into color, aerial images into maps, sketch image into original photographed image, and so on. These are all examples of translating one image as you wish, as per your wish. Okay. Could you please mute? I can hear a lot of noise from your end. Some participant, you need to mute yourself.
அப்படியே வெச்சிட்டு வாங்க, வந்து பாத்துக்கலாம். எங்க போகாது.
Kindly mute yourself if you are not asking any question. Can you mute yourself, please? Hello, is there anybody from the host side? Yeah, thank you for muting. So Pix-to-Pix is another this sort of image-to-image translation system. Similarly, we can have nowadays, this is a fun application from this few-shot adversarial learning of realistic talking head model. So you can give any expression of your face and it can copy that expression, not your face, but only that expression, happy, sad, angry, some emotion that is reflected by your face will be copied and will be imposed on a very nice cartoon character or an archival quality photo like the Mona Lisa photo, how Mona Lisa would look like if she imitates your facial expression. So this sort of many such kind of stuff can nowadays be done very easily with this GAN-like architectures. And image-to-image translation is one of the most state-of-the-art, applications of GAN. So that was about generative adversarial networks. It's just some rudimentary things, and you should take away the final gist that a GAN network, a generative adversarial network, consists of two neural networks actually, one generator and one discriminator. These two networks are in conflict. They are playing a two-player zero-sum game with each other. They are kind of in a tug of war, and in this, all competitions are not harmful. Through this competition, both the networks actually improve each other until they reach a stage where from no further improvement is possible. That stage, in language of game theory, we call it Nash equilibria. In practice, there are a few downsides of GAN also, like the mode collapse problem, where the same object could be generated again and again, and the variety of the generated objects may be missing. Then GANs are also very much training data savvy. Unless you provide lots of training images, you need to show it lots of example training images. It cannot easily generate such nice quality. The quality of images I have shown to you, they were obtained after huge computational power being, wasted on training the networks. So increasing the efficiency over low resources computing for GAN-like systems, like if I want to train it on a mobile handset, can I do that? So that is another very important research facet these days, how we can train a generative adversarial network with limited computing resources or similar generative networks. Now let me switch to the next part of the session, after which I will take your questions. So this part I want to, just basically summarize some very important aspects of practical machine learning algorithms when they are devised in practice. Because ultimately, machine learning survives because of its good results, and such results could be obtained with very cautious undertakings. So this is the title of the talk, as you can see. Do your data behave gently with your machine learning algorithms? What if not? It's a very important thing. So data has a lot of things to do before sometimes we are under the wrong impression that if we have a lot of computing facilities, Python programming programs, all the state-of-the-art machine learning models from ICML, NeurIPS, CVPR, etc. at our disposal, we are equipped to solve any problem. We can predict how much Omicron infection will go on, for how many days. We can do a lot of data analytics on many other things, correct? But that is not the full picture. The problem is sometimes the real world data is plagued with different varieties of irregularities, non-ideal characteristics, which greatly affect the effectiveness of all machine learning algorithms. So the data can be very much irregular, very bad. What will you do under that situation? That's what we are going to discuss. So I'll just skip some of these slides because you already know that. Yeah. So this is typically a self-driving car where a classifier is actually employed. And the camera, there is a backend classifier which will classify the pedestrians, and it says, okay, this is a traffic light with 75% chance, this is a pedestrian with 99% chance, and so on. So you see the world ahead of the self-driving car like Tesla 4.0 is seen through this sort of classifiers. And sometimes the classifiers can take pictures at certain intervals of time and put them into different heat maps. The red ones are pedestrians, blue ones are cars, and so on. Now, in case of gentleman data, we assume that all classes are equally represented in the training set. That means if you have a medical image data set where you want to classify, let's say, lung X-ray images once again, and you need to identify those images in which there are off-white spots visible in the lungs. These are called nodules. And if nodules are formed in your lungs and you are a smoker, then your days are really, really limited. You are going to have lung cancer. Okay. So unfortunately, what happens is, fortunately, what happens is, I should tell it in reverse way. If you randomly sample 100 people, including smokers, you will get the disease class or the nodules, maybe in 3-4 of them. Rest 96 will be benign. But the machine learning system, so your training set will have lot of examples from one class, but very few examples from the rare class, the target class, like the nodule class, the cancer class, which you want to detect, right? So what happens is the machine learning algorithm, then I have listed a few ideal assumptions, and the first assumption is wrong. All classes are not equally represented. In that case, the machine learning algorithm will make various errors in its prediction. The second point, you see, actually the data which obeys all these points, that data could be called as a gentleman data. And the machine learning algorithms will work very well on such data. So all the sub-concepts within a given class must be equally represented. What does it mean by sub-concepts within a class? Like, these are like subgroups within the class, clusters within the class. Like, you want your machine learning algorithm to distinguish between apples and oranges. Now, within the apple class, there may be green apple, red apple, reddish yellow apple, yellowish red apple, so many types of apples. If you do not cover, when you are showing the training data to your machine learning algorithm, if you do not cover these internal variations adequately, the machine learning algorithm may not understand some of these internal sub-concepts if they are not present in the training class, but they appear during the testing or validation. The third point says all the classes must have similar class conditional distributions. One distribution is elliptical, the other distribution is very much skewed or circular. If that happens, this will badly affect the prediction of the machine learning algorithm. Fourth and fifth point says all the features are defined for all members of the dataset. Values of all the features are known for all the data instances in the dataset. If these are violated, then we say feature-based irregularities are coming into picture. Life is hardly so easy. So one or more of these assumptions are very frequently violated by the data that we take. Based on such violations, we propose a nomenclature of data irregularities. If you look at this survey, it's a very famous survey by our group, handling data irregularities in classification. Data irregularities could be of two types, distribution-based and feature-based. Among the distribution-based irregularities, we have class imbalance, class skew, small disjunct. The first three assumptions in the previous slide. First one violated, that is class imbalance. Second one violated, small disjuncts. Third one violated, class skew. And the fourth and fifth assumptions give rise to feature-based irregularities. So if all the features are not recorded because of equipment failure, sensor device malfunction, then we have missing features problem. On the other hand, if some features are not defined for some classes, like the marital status in a sample survey, whether married or unmarried, that is not defined for students up to class 10, because for them it doesn't matter actually. Or similarly, the employment status or the employment type, whether salaried or self-employed or business, that doesn't matter for a student of a primary school, right? So these are typically the absent feature examples. Okay, some features are not defined or not meaningful for some of the data items. When such data irregularities come into picture, your classifiers will look like these confused cats. Okay, they will make all wrong predictions. So you need to be very aware of it. In fact, most of the traditional classifiers, neural networks, for example, who fears whom? Most of the classifiers are very much sensitive, allergic to these data irregularities. The neural networks are very sensitive to class imbalance, small disjuncts, absent and missing features. Key nearest neighbors, they are sensitive to all others, but they are quite immune to class distribution skew, because key nearest neighbors do not make, they are non-parametric classifiers. They do not make any assumption on how the class density is distributed. Bayesian inference is sensitive to class imbalance, small disjuncts, class distribution skew, absent features, etc. Decision trees, if you are familiar with decision tree algorithms, they are inherently immune to feature missingness because they never use all the features sitting together into a feature vector. Random forest or decision tree classifiers always start building from a random subset of features. That's why, but they are affected by other things like class imbalance, class distribution skew, etc., etc. If we look at the class imbalance problem, just hold on for a second. Hello. So the class imbalance is basically separating two classes, the majority and the minority classes, and usually one of the class is greatly outnumbered by the other class. You can see here, these blue points are so many of samples from the blue class. So this is the majority class. And these points are from the minority class. Usually the classifier is biased towards the majority class and tries to put all the minority samples into the majority class as well. Lot of real life examples come into play. For example, credit card fraud detection. In fact, if you look at the number of credit card transactions per week, it could be of the order of 2 to 3 crores, even in this post-COVID period. On the other hand, the number of fraudulent transactions is only 5,000 to 6,000. So see the difference. On one side, we have 3 crore, and on the other side, we have only 5,000. It's huge. Similarly, detecting uncommon diseases which are present, only a few sick persons versus a lot of healthy persons, and so on. These are all examples of class imbalance. And when such imbalance arises, it's like you are preparing for an exam tomorrow. You have 2 chapters in syllabus, limits and continuity versus permutation combination. You practice only 3 sums from permutation combination and 100 sums from limits and continuity. So next day in the exam hall, you will be very confident about the sums coming from limits and continuity chapter. You can attack any unseen problem, but for the permutation combination unseen sums, you are very disconfident. You start panting, puffing, turning pale because you didn't practice much. Same thing happens with the machine learning algorithm also. Since it hasn't seen much of the data from the minority class, it starts making lots of mistakes. Okay. So this is, so one class is greatly outnumbered by the other class. Although, so this picture is a funny representation which says this class is much more important. Its weight should be much bigger because this is the target class, the cancer class, the fraudulent transaction class, the anomaly detection, the anomalous the data samples class. So this minority class is actually very important. Okay. Then again, if your training data is biased, first of all, this dotted boundary is basically the ideal decision boundary, which minimizes the Bayesian risk. But if you have a class imbalance data set, these two ellipses denote the spatial distribution region of the two classes. So the classes, the red class can actually span over this blue circle, and the blue class can actually span over the red circle. Now the training samples of the blue class have been taken more or less uniformly from the entire data space. This is called unbiased sampling. On the other hand, the red class not only is minority, but it is also biasedly sampled. For example, you need to opinion polls. All of us know about opinion polls. Nowadays, lots of discussions are going on the UP election 2022 opinion polls. During the opinion polls, you need to go to randomly sample 30,000 people from a constituency, or maybe 10,000 people from a constituency, and ask them whom they want to see as their next chief minister, etc., etc. Now, if you select these sample people whom to ask from a particular area, or only from a particular class of government officers or class of police people, then your sample set becomes highly biased. Their opinions will be skewed. Although all of them will probably go for a single person, that choice doesn't reflect the general opinion of voters of a large constituency. That is biased. So these points are taken only from this region, so they are biased samples. Now, if suppose you apply a support vector machine classifier or similar linear classifiers, it will put its decision boundary in this way. Okay, and it's a biased decision boundary. Therefore, when during the testing or validation, when new points come like this, all these points will be misclassified. Because the rule of classification is left side of this linear boundary is red class, right side is blue class. So if your classification boundary is this one, then all the points on the right side will be classified to belong to the blue class. So you see, all these points which are well within the red class now will be stamped to belong to the blue class. This is the problem. Now, sometimes the relative abundance versus absolute rarity also matters. Usually the number of points from the majority class divided by the number of points from the minority class, that is called imbalance ratio. If the minority class has 1,000 points only and the majority class has 10 lakh points, still the minority class, if these 1,000 points are more or less unbiasedly sampled, still the minority class could be learned. The imbalance ratio is 1,000, but if the imbalance ratio is 1,000 in this way, where the minority class has only 1 point, the majority class has 1,000 points, in that case, only from one training data, what could you infer about this region of distribution of that class? Nothing. You can learn nothing if there is only one training example. Okay. Spatially, probabilistically, your classifier will just then be a random classifier. And it's a matter of luck how many points it misclassifies. So absolute rarity is another big issue. I have already talked about unbiased and biased sampling. Now, confusion matrix, just to recapitulate things. It's a matrix that systematically tells us how the results are systematically provides the results of a classifier. Many of us know that, the confusion matrix. And we know that, okay, for the confusion matrix, we have these diagonal entries as true, negative. Classifier says no, and they really do not have the disease. And true, positive. Classifier says yes, and they always have the disease. In fact, you see, in case of two-class classification problem, ironically, positive is a very negative word. We all know that, right? When we say COVID positive, actually, it's a very bad news. It's a very negative news. But that's the convention. So you see, usually we define this sort of performance indices for a classifier: accuracy, true, positive, rate. When the classifier, when the data class is actually yes, how many times the classifier predicts yes. TPR is also known as sensitivity or recall. Similarly, we can have TNR, which is actually specificity. Now, it could so happen that, suppose, okay, so this is how we calculate the different, this sort of different measures for the classification. Now, suppose you have 100 samples from class 0 and 10 samples from class 1. This is your machine learning model. It's a two-class classification problem and highly imbalanced. So this machine learning model says it correctly predicted only 2 points from class 1 to belong to class 1. All the rest 8 points from class 1, which is the minority class, to belong to class 2. On the other hand, all the majority class points are rightly classified. So what is its accuracy? Overall, it misclassified only 8 points. So its accuracy is, of course, 92 by 100. That's 92%. So accuracy is 92%. Precision, which is basically how many positive classes it has rightly inferred. Precision is 1. Recall is basically for the 1 class. So that is quite poor. 2 by 2 plus 8, 0.2. And F1 score is 0.33. So to quantify, so you see, your classifier can have a high level of accuracy. Still, it could completely miss the minority class. That's where G-mean-like indices come. G-mean is such an index. What it does is, suppose there are 96 negative. So what is G-mean? G-mean is basically an index which is the geometric mean of sensitivity and specificity. Suppose there are 96 negative class samples and 4 positive class samples. So the classifier predicts all samples in negative class. So the accuracy is 96 by 100 or 0.96. TP or true positive is 0 because all samples have been, all 4 positive class samples have been predicted to belong to the negative class. This is your confusion matrix. So you see, although the accuracy is 96%, the G-mean is 0. But if it predicts 96 in negative class and 4 in positive class, in that case, G-mean is 1, which is happening here. So there are a lot of techniques to remedy class imbalance. 2 such techniques are very easy to understand. Oversampling, where we generate artificial points inside the minority class to make it equally populated as the majority class. SMOTE is one such technique, very old technique by Nitesh Chawla et al. It's called synthetic minority oversampling technique from 2002. And it has also some good and bad sides. In machine learning, nothing comes without a price. Similarly, we have undersampling, where we downsize the majority class. We just delete some points from the majority class so that the 2 classes have equal size. One such technique is the random undersampling. Other than that, we have cost-sensitive methods where we give an adaptive penalty for misclassifying points from the minority class. Severe penalty will be imposed. For misclassifying points from the majority class, not that much penalty will be given. So over and undersampling are usually called data level techniques. They rebalance the data, as you can see here. The original data set, the majority class is downsized in undersampling. The minority class is synthetically populated in oversampling. So what happens in SMOTE is that the synthetic minority oversampling technique, we take one data point from here and then from the minority class, and then we select a few of its nearest neighbors, maybe 5 or 3 nearest neighbors. Among the selected 3 nearest neighbors of that minority class point, they are also from the minority class. We select any j of them. Suppose out of 3, we select one minority nearest neighbor at random. Then we simply use a convex combination of these 2 points. One is the target point xi, and one is the randomly selected nearest neighbor xj, and alpha is some number between 0 and 1. So the new point, if you combine 2 vectors in this way, 1 minus alpha times xi plus alpha times xj, you get a new vector on the line joining these 2 vectors. That's what we are doing here. Oversampling, for example, if we are using 5 nearest neighbors and the amount of oversampling needed is 200%. So for every sample, we need to generate 2 more. So only 2 nearest neighbors from the 5 nearest neighbors are randomly chosen, and 1 sample is generated in the direction of each of these neighbors. This is SMOTE. So this is an actual run of SMOTE. You see this red class is the minority class. When you do SMOTE, you see this sort of generated points. But SMOTE can also lead to overgeneralization. It can actually delete many majority class points erroneously. Sorry, it can actually confuse the learner about the distribution of the overlap between the minority and majority classes. In fact, SMOTE, when hybridized with Tomek links, that is sometimes very effective. What are Tomek links? These are basically pair of points of which one is from the minority class and one is from the majority class. So what we do is we can first do a SMOTE to overpopulate the minority class. Then we can identify such Tomek links and we can simply delete these Tomek links, these pairs, which will actually increase the separation between the 2 classes. The more separated the 2 classes, more accurate the classification will be. So this is an example of SMOTE plus Tomek link. You can see these blue points are from majority class, red points from minority class. We can use SMOTE to artificially populate the minority class. Then we can identify these Tomek links by checking the pairs, and then we can simply delete the Tomek links. Then we have a much better distribution of the 2 classes. Random undersampling, what we do is we can randomly select a number of points from the majority class, and we can simply, like these blue points, and we can simply delete them. But here we run the risk of lacking or forgetting the information regarding the distribution of the classes. Sometimes we can undersample based on, we can delete those majority samples, most of whose k neighbors are minor. For example, minority class, belonging to the minority class. So this orange class is the majority class. We can select these points. You can see my cursor. We can select these points and check their 3 or 4 nearest neighbors. If we see, okay, it's a majority point, but 3 out of 4, 3 of the neighbors are in the minority class, then maybe this point is well gathered inside the, well penetrated inside the minority class, and it's better to delete it so that the classifier may not get confused. So what we do is we simply delete these such points. This is and undersampling with edited nearest neighbor philosophy. So this is what happens during oversampling and undersampling in a real-world data set. We could do data augmentation as well. That is also a very interesting technique. When you have class imbalance, oversampling performs like this, undersampling performs like that. But data augmentation means you can perturb the minority class points by different means to generate more points in similar minority class. I can hear a lot of noise. Kindly mute yourself. Who is the host here? Could you please mute? Lot of noise now. Could you kindly mute? Hello. It's impossible to continue in this way. Kindly mute yourself. Who is the host here?
We are checking, sir. No one we are getting.
Now the person is muted. I can see Soumya Ranjan from his side. Lot of noise is coming. So the host should remain aware of these things. Anyway. Okay, I will go on for next 5 to 10 minutes and then conclude. So this data augmentation also goes like this. You can perturb some of the minority class points. And so from the host side, there should be some persons who can mute the other, this sort of participants who are creating noise. So the data augmentation goes like that. You have minority class points and you can perturb them to create other similar examples from the minority class. That is not exactly oversampling or undersampling, but that is data augmentation. Cost-sensitive learning, in fact, modifies every classifier works on an optimization objective function. So the cost-sensitive learning modifies that objective function so that when the training errors are made on the minority class, they may be severely penalized compared to the majority class. So this is, I am not going to explain the mathematics behind it, but this is the near Bayesian support vector machines for class imbalance learning, where actually the objective function of a support vector machine classifier was modified with unequal weights for misclassifying points from the minority and from the majority classes. Okay, those unequal weights have been shown here by these symbols. I will end up with a simple example of class imbalance learning system with reference to a k nearest neighbor classifier. The k nearest neighbor classifier actually, as we know, it carries the training data on its back, and when a new data point comes, it examines the nearest neighbors of that data point, and it infers that class for the new point to which most of its nearest neighbors belong. So if all your friends are very genuine and sober and good, then you are also very genuine and sober. But if your friends are not that good, if they're rowdy, if they're like mastans, goons, then your character is also very dubious. That's the thing. So I will explain one imbalance handling mechanism based on this k nearest neighbor philosophy, which is the most understandable classifier for all of us. And it's a very interesting classifier which could handle multi-class, not only two class, but multi-class class imbalance handling. Suppose, and this paper was published in the IEEE Transactions on Neural Networks and Learning Systems. Suppose you have C classes in your training set. So the ideal probability of occurrence of any one class is 1 upon C. If you have 3 classes, the ideal probability that when you randomly pick up a point, it will belong to one of these 3 classes is 1/3. But practically, the practical probability, the original probability is NC upon N. What is NC? NC is the number of points belonging to the Cth class. So the probability of occurrence of the Cth class is NC by N. Now what we do is, when we count the nearest neighbors belonging to different classes, we do not give equal weightage to the counts of the 2 classes, but we multiply these counts with a weight. That weight is the calculated class specific weight. What is that? R by PC. If PC is equal to R, that means all the classes are equally presented. See, if there are 2 classes, R is 1/2 and 1/2 for both the classes, ideal probability. If there are 50 points from each class, then PC is also 50/100, which is half, equal to R. So for both the classes, the weights are same. WC is 1. But if one class has very less number of points, only 10 points from one class and 90 points from the other class, R is half and half for both the classes. But for the majority class, PC is 90/100, 0.9. And for the minority class, PC is 10/100, 0.1. So the weight for the minority class is 0.5/0.1. R is 0.5, which is 5. And the weight for the majority class is 0.5/0.9, which is 5/9, a little more than half. So you see the 2 class weights are different. The more there will be, class imbalance, the more weight will be given to the minority class. It's a very simple thing, almost a folklore method. So this is how GIHS stands for the Global Imbalance Handling Scheme, which is based on the cost sensitive learning. And you see what we are doing. Suppose there are 20 points in total in the training set, 16 from the red class, 4 from the blue class. Blue class is, of course, the minority class. So their ideal probabilities are 0.5 and 0.5. Now a new point appears here. 3 of its neighbors belong to the red class and 0 number of neighbors belong to the blue class. So the count is 0 from blue class, 3 from red class, and the revised count will be obtained by multiplying with these weights. Now you see the ideal probability, practical probability for the blue class is 4/20, which is 0.2, and for the red class is 16/20, which is 0.8. So our W, if you go back, what is W? It is R by PC. So for W for the blue class is R 0.5 by PC, which is 0.2, 2.5. And W for the red class is 0.625. So we multiply these counts with these weights. In this case, this diamond is certainly in the blue class, but in this case, these are the problematic test points which appear near the overlap region of the 2 classes. So in this case, 1 point comes from the blue class and 2 points come from the red class. If I multiply these numbers with these weights, we have 2.5 and 1.25. So the revised count indicates that this point should belong to the blue class. So you see a vanilla KNN, a normal plain KNN, will classify this point to belong to the red class because 2 of its neighbors are in the red class. But this special KNN will put this point into the blue class because the revised count indicates there is a high possibility that this point is actually in the blue class. Around itself, maybe there are other blue points which are not present in the training set, but which could be there in the original full data space. Okay. This point is certainly in the blue class. That is because no neighbor is in the red class. So this is the performance on a number of data sets, 25 two-class classification data sets, and in terms of the G-means and compared against many other class imbalance learners. Class imbalance is very much there in the deep learning era. Sun 397 dataset is a long-tailed, which sometimes nowadays it is called long-tailed classification. Because in the histogram of the classes, presence of a long tail means some classes appear very rarely. And there are a lot of methods. One such method which we devised long back, I think not long back, sorry, in 2019, now but 3 years is long. And this paper also appeared in the same ICCP conference, 2019, it's called GAMO. So what we did is, we are using the generative adversarial network. In fact, in the deep learning era, please mute. If you are asking a question, please go on, otherwise please mute. So in the deep learning area, the generative adversarial minority oversampling, basically what it does is it is artificially populating the minority class in image classification by using a 3-player, 3 neural network based GAN architecture. Okay, so just let me put the idea here. What we do is, this is the unaided classifier. This blue one is the majority class, this red one is the minority class. The class distribution is very complex, non-convex. Now the unaided classifier learns the decision boundary like this. If we use a convex generator plus classifier, the convex generator generates such points which are actually which should be very tough to be classified by the classifier. In this way, the convex generator learns to generate these new green points within the convex hull of the minority class. But here what happens is a lot of blue points are also misclassified. GAMO uses 3 neural networks inside it. One is a convex generator, one is a classifier, and one is a discriminator. The discriminator actually uniformly divides these newly generated green points inside the class, and as a result, we have this sort of nice distribution of the 2 classes, and the decision boundary of the classifier now learns almost the accurate demarcation between the spatial region of the classes. This way, GAMO achieves very good state-of-the-art result. This is the entire GAMO architecture. You can actually view this. There is a YouTube presentation also, and there is a where are we? Okay. Let me just get back. You can view this ArcZIF paper, which is readily downloadable freely. And you can see the corresponding GitHub repository given in the paper where all codes and data have been made publicly available. In machine learning research, most of the participants should be researchers actually. So in case of machine learning research, whenever you propose anything, I'm almost at the end of my talk. Whenever you are proposing anything, whenever you are publishing a paper, make sure that all of your codes and data are publicly available for others to use. Do not try to manipulate the results in order to publish a paper only. Try to make all your codes and data available for others to replicate to get the similar results. In that way, you will actually achieve a lot of recognition and citation as well. So with this, I will actually conclude from my side, and let me hear questions from your side if you have. Now you can unmute and ask me questions. Actually, in between there were a lot of noises. That's why I could not also understand what is happening. So if there are any questions, you can ask. Any question from anywhere. Obviously related to this workshop. So do you have any questions? Any of?
Excuse me, sir.
Yeah.
Sir, in that KNN example, how the weighted value was calculated? That is not clear to me.
Okay. Let me repeat it once again. Let me share. Yeah, first of all, you see, if we have 3 classes, let's say, so ideally in your training set, there should be equal number of members from all the 3 classes. So if you pick up any one point, it is equally likely to belong to one of the 3 classes. So the ideal probability R is 1 by 3, as it is written here as 1 by C. But practically, different classes will have different number of representatives in the training set. So the original probability of appearance of a class is NC by N. NC is the number of points from that class. N is the total number of points in the training set. Do you agree with me? See, if you have a box full of red balls and blue balls, maybe 10 balls in total, 8 red balls, 2 blue balls. So if you pick up a ball at random, what is the probability that it's a red ball? 8 by 10. What is the probability that it's a blue ball? 2 by 10. So that is the exact way in which we calculate the original probability. And the original probability, as much it deviates from the ideal probability, that means the distribution of the data becomes imbalanced. Okay, so ideally, if the data is balanced, 2 classes, ideal probability half and half. 5 points from each class, original probability 5 by 10 and 5 by 10. That is also half and half. No problem. But if the data is imbalanced, then the original probability and the ideal probability will be different. So in that case, we calculate the class specific weights in such a way that the minority class gets more importance. So the class specific weights are R by PC, where PC, if so, for the minority class, PC is less. PC will, because NC is less, NC is the number of points from the minority class. So NC will be less. As a result, PC will be less. If PC is very small, then R by PC will be very high. And the weight from that class will be very high. So weight of a neighbor from a minority class is very high. So what we are doing in the nearest neighbor example is basically, you see, in practical life, what we do, we all have some nearest neighbors, 2, 3 close friends, husband or wife, parents, they are the nearest neighbors. Now, but then when we take the opinion of our nearest neighbors, who are emotionally, geographically our nearest and dearest, when we take their opinion, do we give equal importance to all of them? Probably not. At some stage, we give our mother's opinion maximum importance. At some later stage of life, we give our husband's or wife's opinion the maximum importance. This way, we grade the importance level of the opinions. Here also, we are doing the same thing. So we calculate first the ideal probabilities, 2 classes, therefore it's 0.5, 0.5, half and half. Then we calculate the practical probabilities. For the blue class, it is only 4 points out of 20. So 4 by 20 for the blue class, and which is 0.2, and 16 by 20 for the red class, which is 0.8. Now we calculate the weights by simply dividing these R values with the P values. For the blue class, R is 0.5, P is 0.2. So the weight of the blue class is 0.5 by 0.2, which is 5 by 2, which is 2.5. And for the red class, it is 0.5 by 0.8, which is 5 by 8, which is 0.625. Now with this weight, what we are doing, we are multiplying this weight with the count of the neighbors from the 2 classes. and we create the revised count. Based on the revised count, we are actually categorizing this point, this new query point. So is that clear? Think of yourself.
Yes, sir. Thank you.
Okay. Any other question?
Sir, can you share previous slides with us?
Sir, in the
Yes.
chat box, there is a question from Dr. Assis. May I read the question, sir?
If deep fake videos exist, can anyone believe digital media? Easily, yeah. That's typically a question. There are therefore the various, like when viruses are made, antivirus also have to be made to capture them. Similarly, there are various ways of filtering fake news and media, fake videos, and these things actually depend on the causality, causal inference, causal learning, and so on. So similarly, an ongoing research area is there which tries to filter and catch up such fake videos and images. It's not very easy task though. So based on the context, based on the time, we do that. In fact, you see, it's more like spam filtering. When you have a spam emails are very often generated. Nowadays, most of the spams are also generated by such generative adversarial network kind of thing. It's not very easy to catch them, but spam filters are also designed to do that. That's a very nice research area. How to do news filtering. Okay, so a news item nowadays in Facebook or WhatsApp, you can have a multimedia news item where you have a video, text, etc. Scanning all these things and looking into the context, how we can say which one is genuine and which one is fake. For that also a section of machine learning research is being undertaken. Yeah, it's not nowadays. You need to be very cautious and exercise human level intelligence to judge what you are looking at, whether it can be right or wrong. It's a good question. Anything else?
Any other questions, participants? I think, sir, there is no other questions.
So I will share my slides through Professor Gyanoranjan Patra, or Professor Mihir Mohanty is also there. I think I will email him the slides. And best of luck to all of you. If you want to ask any offline question also, you can drop an email to me. I probably shared my email ID in first slide, or you can take it from the organizers also. Okay.
Thank you, sir, for this interesting and wonderful talk. I think Professor Mihir Mohanty is here. Mihir, sir, do you want to share anything?
Yes, sir. Thank you very much, Professor. Really, it is now most informative. Yeah. Yes. Thank you so much.
Thank you.
You have taken so much of pain because of.
No. I also had, for me, you had to reschedule it in the last time. Thank you very much for that.
No, that's
favor. Because I actually, my whole family got COVID infected, and we are still having to manage things for the elderly parents and all. That's why I had to shift a few things here and there.
Okay.
I hope all of you stay protected, take care, because it's a really bad time we are passing through. I hope it will soon pass and we will all able to meet physically at some point of time. Thank you all.
Okay, thank you very much.
Thank you very much, sir.